Recall in Module 2, Lesson 8, when using too short of an exposure time, adding spectral frames together does not increase the signal-to-noise ratio if the spectral signal is not above the noise floor of the detector. The source of noise is to acquire for a longer time or use higher currents. However, as we increase the amount of current, we increase the risk of sample damage. This means that with a direct detection camera, we can sum several sparse spectral frames together and still achieve a high signal-to-noise ratio. As an example, I will choose a longer view time of 0.34 seconds and observe the signal-to-noise ratio on the spectra. I can clearly see the oxygen K edge. Now when I reduce to the shortest view time, which is a factor of 3 shorter than the previous view time, each frame becomes noisy, and above 600 eV, there is too little signal in the spectra to detect any edges. However, if I add 1,000 frames, each acquired at the shortest view time, I get the same SNR as the longer view time. We can overlay the two spectra acquired with two different view times, but the same effective acquisition time. We see that the spectra are identical. Furthermore, if we go to the higher energy silicon K edge, we can clearly see the edge in both spectra. This would not be the case for an optically coupled camera, especially when operating at the fastest frame rate. Since we can add spectral frames together without paying a noise penalty, we can change the way we acquire our EELS spectrum image. Now we'll go back and reacquire the spectrum image, but I will reacquire the data over multiple spectrum image frames. This will refresh the stem image to make sure that the sample is not moved during the course of acquisition. I'm going to keep the spectrum image size the same, but I'm going to change the dwell time to 330 microseconds, which is the fastest frame rate of the camera. Then I'm going to change the number of passes from 1 to 100, which will give us the same effective exposure time as the previous spectrum image, where I used a 0.03 second pixel time and 1 pass. Since we are acquiring the spectrum image over 100 passes, we need to change our drift correction method. If we use the same frequency of every 100 rows, the acquisition time will take 2 hours. I'm going to reset the drift measurement so that the continuous drift correction is enabled. This method will still use a reference area that you specify for the initial measurements. I'm going to place the initial reference area in the same region as my previous acquisition. Once 2 spectrum image passes have been completed, the drift measurements will be performed using the ADF image acquired from the spectrum image ROI highlighted by the green box. Sometimes we will refer to this ADF image as the simultaneously acquired ADF image. The drift measurements will be applied to the end of each pass without the acquisition having to stop. This cuts down the acquisition time. I'm going to keep the dimensions of the spectrum image the same, and then I will click Capture. First, the initial drift measurement will be made. Digital micrograph will measure the drift rate within a 30-second window so that the drift correction can be applied while the first 2 passes are being acquired. Within a few seconds, we have an almost complete picture of the sample within the ROI. We can still use the Spectrum Picker tool to investigate specific areas of the ROI as the data streams into digital micrograph. I can start identifying edges in my sample by examining the position of the edges in the spectra. Most apparent is the oxygen K edge. If I go to a different feature and I go to higher energies, I find the tungsten M edge. Also note that the drift images have changed after the second pass is completed, and the drift measurement is being performed using the simultaneously acquired ADF image. Since we are now using the multipass workflow, we can calculate live elemental maps of the entire sample region as the data is being acquired. This is the same method that is used when acquiring EDS elemental maps. In the SI tool palette, I can click on the periodic table icon to show a table of the elements and their associated edges. Live elemental maps will be generated from the elements highlighted in blue. If I want to select an element, I can left-click on an element and select the desired energy loss edge to analyze. For example, if we look at titanium, I can choose the K, M, or L edges if they are within the spectral range I have chosen to acquire. For this measurement, I am choosing the titanium L edge. Once I'm done choosing the elements, I click OK and the live maps are instantly calculated on a separate workspace. The initial maps may look grainy, but as the acquisition continues, the quantification calculations will be refined and the elemental maps will have the same resolution as the spectrum image. Having the elemental maps is a nice way of determining if the acquisition needs to be continued or if there's a sufficient amount of signal to determine the distribution of each element in the sample. As the acquisition proceeds, I can monitor the amount of time by looking at the timer on the left-hand side of the spectrum image palette. We can go back to the workspace where the live map is being stored, and we can see through the drift images that the condition of the sample and how it compares to the original image. This constant feedback allows us to maintain the integrity of the sample and the data. At the bottom right-hand side of digital micrograph, we can monitor the number of passes that have been acquired. If there needs to be more or less passes, we can go back to the spectrum image tool palette and adjust the number of passes accordingly. As we make adjustments to the total number of passes, the timer in the palette will also change to reflect the amount of time left in the acquisition. If I go back and look at the elemental maps, even after 10 passes, I have a good enough contrast in the maps to observe all of the elements, and I will stop the measurement. Once I click the capture button again, a dialog box will be prompted saying that the acquisition will stop at the end of the current pass. If you want to keep this dataset, let the pass finish. If the dataset is in some way compromised, click the abort button immediately. When the acquisition stops, the maps will be recalculated with the dark reference applied, and we can see we get high quality maps after only 4 minutes of acquisition. If we were doing a single pass, we would still be less than a quarter of the way through the acquisition, and we would have no feedback on what the entire elemental map would look like. The first multi-pass spectrum image was acquired with single EELS. The advantage of using single EELS is we can go much faster since we are only acquiring one spectral range at a time. With dual EELS, we must acquire 2 spectra at each pixel, one low loss and one high loss spectra. However, now we can deconvolute thickness effects and we can use the ZLP lock feature. The ZLP lock feature can be important when acquiring multipass data, especially if there are any stray fields in the room or if the operator is sitting next to the microscope and happens to move their chair during the acquisition. Next, I'm going to select View on the EELS palette to check that my live time is set correctly on my low loss spectrum. I see that the spectra is turning red and yellow, which means we are outside of the linear counting regime. Now that I've reduced the live time to 0.05%, the low loss spectra is green and suitable for acquisition. Since I'm collecting a dual EELS pair at each pixel, I need to allow for enough time to acquire both spectra at each pixel. Each frame takes 334 microseconds to acquire, and we need to allow for one additional blank frame to clear the data from the previous frame. Therefore, I will set the pixel dwell time to 1 millisecond in the SI acquisition palette. This will increase our total acquisition time, but it will allow us to calculate the absolute elemental concentration, and it will have absolute energy scale calibration by using the zero loss peak as a reference. I will keep all of the ROIs in the same area and start the acquisition. We notice that the scan rate is slower because of the longer pixel time, but we are still able to monitor the live elemental maps. Based on our last map, I'll reduce the number of passes to 30 and see how the signal-to-noise ratio progresses. If I move the drift reference out of the way, I can monitor both the low loss and the high loss part of the spectra as the data comes into digital micrograph. Now I will monitor the signal-to-noise ratio in the elemental maps and stop the acquisition once I observed a high enough contrast to see the distribution of each element in the elemental maps. This concludes the lesson on acquiring a spectrum image using the K3 camera through multi-pass acquisition.